Okay, so let's continue. The next speaker is Ruijie Xu. Ruijie Xu. We talk lattice works as an exactly solvable model. Let's start.
Okay, thanks for the introduction. So it's the last talk today, and I'm going to talk about something maybe stays between integral systems and also probability theory and also combinatorics. So I think the exact research field of this lattice work problem is actually called analytic combinatorics. So analytic combinatorics. So what I'm going to talk about is about using some analytical way to solve some combinatorial problem. It's a bit strange maybe, but it's some problem. No, some research fields that is not very well known, but still there are some people working on this. So let's start from a simple random walk model. So I think you may see this you may see this model in some undergraduate probability theory courses. That is, we can construct a discrete random walk on positive x-axis and start from some point on this x-axis with probability p jumping forward and y minus p jumping backwards. So what is the probability that it will always return to x equals 0? So in a probability class, the professors will tell you that phi1, which is this probability, equals 1 minus p plus p phi 2. This can be just interpreted easily by some combinatorial idea or probability idea. Just the probability there's 1 minus p probability to jump from the x equals to 1 back to 0, or it jumps to the x equals 2 and then jump twice to the origin. So now we can see that this gives us a quadratic function, and this quadratic quadratic equation has two solutions: 1 and 1 minus p over p. So there is a question which may also appear in the probability class. It's just we need to find a single argument to show that phi1 equals 1 minus p over p when 1 minus p is less than p. This actually is very intuitive in probability, because when we try to jump forward, we have larger probability to jump forward, then this should be less than 1. But I'm not a probabilitist, so I don't know how to prove it rigorously. But there is a simple combinatorial idea. Let's formulate the equation with an extra small parameter t, which counts the number of steps. Then our equation is still quadratic, but it has the parameter t here. So we know that solution is actually this. But after introducing t into the functional equation, our solution becomes very complicated. But if we consider this solution as a formal series, that is formal series of t, that is actually the Lorentz expansion of this solution near the origin, then we can see that we have two roots. One root is actually a formal series of t, but the other roots actually at t equals 0, it is a singularity. Or we should say combinatorially, it is not a formal series. Then we can immediately know that we should choose this phi1, 1. This phi1 actually represented 1 for the probability p, which is less than half, and also 1 minus p divided by p, which is the probability of larger than half, and it will finally jump to the origin. So we can see that the algebraic property in CT determines which root we will choose. And actually, no matter how p changes, we always choose the same root. So that is some kind of basic idea of the analytic combinatorics. So we're trying to solve the lattice walk. We're trying to treat random walk as an enumeration problem. And we try to calculate the number of configurations or the genetic function. And actually, we focus on the algebraic properties of roots and also its genetic functions. and also many different properties. So what actually in my study is the study of lattice work. The probability P is ignored. So in the future talks, there are no probability at all. And the random walk becomes the lattice walk. And also on contract, in the later, all the functions contains T as a parameter. So although I won't always write T in the function equation, but the T is there. Also, there are other ways to get a lattice walk from an integral system or from a math basis model. But what I'm going to talk today will focus on this algebraic process. So this idea in combinatorics is exactly called the kernel method. Here's another very simple beginning example. So this is, I think, everyone staying here should know this is called the deck path, which is a very famous model in combinatorics. And we know that the number is called the cat number, just the number of configuration. And we know that deck path actually satisfies this quadratic function, ct equals 1 minus t squared ct squared. So this can be constructed by some purely combinatorial idea with some combinatorial techniques. But can we do this actually by a more general or more, how to say, more machinery way? So we just consider this random walk as a walk like on the first quadrant and write down its recurrence relation. And we know that we have a boundary. So the recurrence relation will have some boundary terms. And we write down the generative function of the recurrence relation as its function quotient. We'll have a boundary term here. Now we consider substitute the roots. So there are two roots here. Here the coefficient of CXC is called the kernel. There are two roots, and still we choose the roots which is a formal series of T, and we immediately got the solution of the deck path. So there are very fruitful results for one-dimensional work, actually. So here, this is the work result done by Brandia and Philippe Flachet. So the P here is a kernel, which is a polynomial, but not necessarily quadratic, but also with larger works. Actually, it's just higher degree. So you can see that all the generative functions we want is actually can be written as a formula of the algebraic roots of this polynomial. Now let's come to a bit complicated, which is the quarter plane lattice walk. So different from the models we talked before. So we have actually, because we have it is a two-dimensional model, so we have x, y, and also our parameter t here. So this is the functional equation that you can get easily. Just write down the recurrence relation of the random walk and construct its generative function. So if we want to apply the idea of a kernel method, the problem is the kernel here, which is coefficient of qxyt, is not a polynomial of one variable. It is a polynomial of two variables. So to deal with this case, the key to the solution is to consider the symmetry of this kernel. So this kernel, if we consider this simple, it's just a simple example, which is this, say, simple random walk in the quarter plane. So the kernel, it looks like a quadratic function divided by xy anyway. So we can treat it as it has some similar symmetry as the quadratic function, that is the Galois automorphism. So for a quadratic function, it has two Galois automorphisms, phi and psi. And we can also write it just as a group transformation acting on this kernel. So phi and psi are two involutions. As this two involution will generate a symmetry group, which is the symmetry of the kernel. So sometimes it generates a group with finite elements, and sometimes it has infinite elements. And also, so for our specific model, it has two roots, y0 and y1, and the symmetry group is very simple. It's just a D2 group. So let's first see some combinatorial approach The first one, which this was first proposed by Professor Murray in 2005. So she finds that if we acting each group element using the group using the group transformation on the polynomial, then adding them alternately, then we can find that this the sum of the right hand side of the function quotient we can get rid of the unknown functions qx0 and q0y, and the solution of qxy can just by taking the positive degree terms and positive degree terms of x and positive degree terms of y of the right hand side. This is a solution which follow symmetries. So how about our original kernel method? So there are two roots, right? So we know y0. So by some calculation, still we try to expand it in the formal series t. And we will find y0 is a formal series of t, and y1 is not. So we substitute the root y0 in, and also the another element which is the pairs after one Galois transform. Then it will give us two equations. And clearly, if these two equations, we can get rid of this q0y. And it will give us a function equation with only qx and q1 over x. And by definition, qx0 is a formal series of x, and q1 over x is a formal series of 1 over x. So we can separate them by just by taking the positive degree term of this function equation. So that is just a simple example for lattice walk problem in combinatorics. So, and also this is also the simplest model. So for some other models, so the idea is nearly the same. Just there are many special techniques inside this because we normally cannot get the solution very easily just by the linear combination. But actually, and also the combinatorics approach only works for models associated with a finite group, but not a group with infinite elements. But actually, if we jump out using the combinatorics approach, we can solve this problem in a unified way, and not only for models associated with finite group, but also for models associated with infinite group. So this is called the Riemann boundary value approach. So the Riemann boundary value approach we are using here is actually the Riemann boundary value problem with Karman shift. That is finding a function holomorphic in some domain L+, and the limit value of which on closed counter are continuous and satisfy the relation. So relation here. So it is a bit different from normal ones. So normal Riemann boundary value problem is that we are trying to find functions which one lives in L+ and one lives in L-, and their limit value is just the value of this side and the value of this side. But this problem is actually, so we have a L+. So we are considering a function phi plus, which is the value of this side of this contour, and also phi alpha plus phi s alpha s plus, which is an automorphism from here to here. Now there are 5 steps to reduce the problem of lattice walk to a Riemann boundary value problem. First, we need to choose treat kxy as an algebraic curve. And currently, we fix t is a fixed value less than 1/4. And now t is fixed. So qx0 and q0y are treated as Taylor expansions of meromorphic functions around 0 in a circle with radius 1/t. Then we can extend the convergent domain from the union cycle to x0, 1, y1, y2. Now we consider a contour, or consider u go around y1, y2 on y plane. Then on the x plane, it becomes a contour on it becomes a contour of x0, y1, y2, and xy1, y1, 2. Since we know on the branch cut of y plane, the function x0, y and xy1 are just conjugates. So we can apply these two these two results to the function equation, and also get two equations similar to what we have in previous. Then finally, by a linear combination, you can eliminate this Q0U, and only Q. So S is here X0 Y1. So only Qx0 and Qx1 U stays. This is actually an equation if we just let phi s equals s over 1. Then it is exactly what the equation not exactly, it looks very similar to what the equation to the result we got in opposite equation method. But actually these two equations actually describe very different things. Now for common type Riemann boundary value problem, there exists a conformal Green function such that Wx is meromorphic, and W phi s minus Ws equals 0 for S in X, Y, or Y2. And it establishes a conformal mapping from the domain bounded by X0, Y, or Y2 onto the complex plane, cut plane with cut. And then with this conformal mapping, we can, it has the inverse mapping is X equals to Fz. And with this conformal mapping, we can get a problem of the standard Riemann-Hilbert problem. It is just something like here. So if we consider this one is the X plane, and the Z plane is just if it on the X plane, this one is we can treat it as X1, Y0, Y1. So on X0, Y0, Y1, the contour goes around this cycle. And on Z plane, it is the branch cut. So what happened here is we reduce a common type of boundary value problem on this cycle to a Riemann-Hilbert problem on the branch cut. Then we can solve this Riemann-Hilbert problem by some standard methods. And the solution is written in an integral form. So currently we have introduced two methods, and these two methods both gives the solution of a codependent lattice walk with associated with finite symmetry group, and also the Riemann boundary value approach can give us a result for problems associated with the infinite group. So what are the relation between these two approaches? The idea is just still the conformal mapping. So let's consider the original functional equation that we directly get from the recurrence relation. So it has two roots, and we can see that the roots inside this y0, we have a term x plus 1 over x. So if we consider the conformal mapping, z equals x plus 1 over x, and also we still use the combinatoric idea, that is, we expand y0 as a formal series of t, and also xz as a formal series of t. So z is just a parameter here. Then we can see y0 and xz, actually 1 is a formal series of z, and 1 is a formal series of 1 over z. So by the functional equation will can be solved exactly by taking the positive degree term of z and the negative degree term of z. Okay. Yes, this x. So we let z equals x plus 1 over x.
What's the meaning? Just a substitution.
Yes. It is a conformal mapping from the unit circle to the whole to the cut plane, to the plane with a branch cut. So the conformal mapping here is acting on the on some plane which represents the algebraic curve of the kernel, but not the original lattice. Okay, no. Then and also, since all the solutions in combinatorics are written with this positive discrete term extraction. And this positive degree term extraction, we know that it can be written in the integral form. And by some calculation, we can recall our solution of combinatorial approach. Here are some remarks. So find the conformal mapping we have here actually glues x0, y1, x0, y1, y2, and xy, y1, y2. And y0, xz is analytic on this cut. And on z plane, the branch cut of xz and yz are separated. So we can see that the opposite kernel method in combinatorics can be treated as a combinatorial version of Riemann-Hilbert problem. And what actually matters here much is the conformal mapping, that the conformal mapping separates the branch cut of these two unknowns so that we can separate these two unknowns by taking counter integral. So, and we can have a thermal to show that the conformal Green function, this conformal mapping is actually differs by a Mobius transform. And also these functions can be interpreted both analytically and also combinatorially. And so this is just these two, this combinatorial approach and Riemann boundary value approach. One thing I may need to say that the Riemann boundary value approach is actually some special tricks. So let's have first look at how we treat elliptic. Let's have first look at what is elliptic approach. So since for our example, the kernel is projecting for both x and y, it is irreducible, and we may consider the kernel as a Riemann surface. And our problem becomes finding meromorphic functions qx0 and q0y satisfying the functional on the whole torus. So the advantage to leave the problem into the onto the universal onto the torus, and is it because the torus has a universal cover, and on this universal cover, the two automorphism, the two Galois transform of the polynomial can be written as just as reflection. Since on the universal cover, the automorphism only have reflection and translation, and these two are, we know that these two are involutions, so they have to be reflection. And the composition is a translation with another period, omega plus omega 3. So if the original torus is parameterized by omega 1 and omega 2, then the second one is this period here is omega 3. So this is a solution which written in a summation of infinite terms, and these terms a, sp, and fiy is the pose of this function. I'm not going to prove this, but I can sketch the proof of it. So probably we know in previous result we have a function like qx0 minus q1 over x0 equals some function, and this is just this function. So it is clearly we can this q0y omega plus omega 3. This q0y omega we can written it as a Weierstrass eta function. But that is not true because Weierstrass eta function can satisfy this relation with a hey, I think here there's a half pi I something like here. But this is not true because q0 omega has its own property. For example, as our definition, q0y is a formal series of y in the units in some circle around 0. So in its convergent domain, it should not have singularities. So if you just use Weierstrass eta function, you need another algebraic function to eliminate these singularities. So here the proof is that he analyzed the singularities of this Fy omega, and he finds that the singularity with Fy omega left to this line, just omega x2, omega x1, is the singularity of this function, and the singularity on right to this line is the singularity of this y omega plus omega 3. I mean, inside the fundamental paragon. Then by some calculation, maybe 4 to 5 thermals, then they can write down the solution of this Q0y by a infinite sum of singularities on the torus. Actually, it may not be infinite. If this omega 3 is maybe k time is a rational time of the original omega 2, because we know that several fundamental domain will cover the original function. But when omega 3 is not a rational function of is not a rational number times omega 2, then this actually becomes infinite sum. Oh, I suppose we should have anyway. So here just some other example about 3/4 walks. So for 3/4, I mean, this is the walk which still the simple lattice walk in 3/4. And the functional equation can be written similarly. But the problem here to apply the analytic idea is that Cxy is defined as a formal series of T with coefficient in X, Y. It is well defined in combinatorics. But from an analytic point of view, it is not well defined, because we cannot have a formal series of both X and Y, right? So I see what's happening. So this page goes earlier before. So there's a purely combinatorial approach, that is by some calculation we can define an AXY is a linear combination of CXY and QXY. So QXY is our original result of total walk, and this CXY is the result we want to know, the general function of walks in 3/4. And this AXY satisfies this new functional equation, and this AXY is algebraic. So the author first got this relation by some obvious sum argument and by some purely combinatorial techniques, but actually it has a very clear graphic or geometric meaning. So that is a lattice walk which cross the x-axis and y-axis back to the first quadrant can be treated as can be reflected to be another walk which ends on the second quadrant and then walk on the fourth quadrant. Then these two actually give us a relation about the AXY, which looks like an obvious sum here. So recently this problem is also solved by an elliptic method. So the idea is that we treat the general function of these three parts as different functions, and still we lift them onto the torus, and by some linear combination we can show the functional equation satisfied here. It seems we can directly apply the conformal mapping method to this functional equation and get the solution. But actually it is wrong. Now you can check it. It is not the right solution, because lattice walk can be just, you can just use a computer to enumerate it. So in the recent work, Andrew Prince shows that we should define a WZ such that WZ is a function or is parameterized by Jacobi zeta function, and also x, y, and z are parameterized by Jacobi zeta function. Then the solution can be written as nearly the same form as what we have from the conformal mapping and the Riemann boundary value problem. That is an integral form. But these two solutions are not solved by conformal mapping or Riemann boundary value problem. So they solve it by exactly checking the singularity of left-hand side and right-hand side, and to see whether they solve the properties of this functional equation and also some other extra properties. So this WZ is actually something that has it has the same pole as XZ in some certain domain, and it has the same pole W minus W Z inverse has some nothing 1 over WZ has exactly the same pole in another domain. So actually I have a conjecture here that the conformal mapping, I mean the conformal Gaussian functions, is actually still our original conformal Gaussian functions. It only depends on the kernel, but not on the area of the work. But the difference is that the AX, BY both have extra singularities inside the unit circle. So we need to consider some extra residues. So the unit circle, because we do conformal mapping, we are working on the complex plane, but not the torus. Now let's come to our last part, which I try to describe some relation between lattice work and integral system. So we have seen that we previously have working on the ordinary generating function of this lattice work. So what about the exponential generating function? So potential generating function is just we add an n factorial here. Oh, sorry, this should not be here. So then by some simple calculation, we will find the functional equation will have a partial derivative here. And if we just consider the generative function any on certain point ij on the first quadrant, it will be something look like this. So this is some equation called mass-based equation. So we can write it more like quantum mechanics. So we consider Fock states. N1, N2 is just Fock's ending at the point ij, and you make this bracket as here and here. Now, and the operator phi I and phi dagger are just the analytic and creation operator. And then we can write a Hamiltonian like phi1 plus phi1 dagger plus phi2 plus phi2 dagger. And the functional coefficient of lattice work is just a eigenvalue function. I'm not exactly working on this, but I find some result which done by other people, which is very interesting. In 2017, Belikov and Malyshev considered lattice work in m+1 dimensional symplectical lattice. So symplectical lattice is just, so if it is a 3-dimensional lattice, you're going to consider lattice work on this slit plane. And the Hamiltonian is written as here. This means that the lattice work should work on the slice direction of, so for example, you are +1 in x dimension and -1 in y dimension. So it is some slice direction. Then for this model, it has L matrix, R matrix, and also the transform matrix is satisfied the RTT relation. And the Hamiltonian is just as a normal integral system. It can be written as a partial derivatives of the transfer matrix. Sorry, here we should not have minus n. And now this model can be solved by a general process of the Benson assets, and we'll have Benson assets equation, and there are many other later to solve that equation. Now I just review some review what I've said today about the lattice walk problem. First, we are talking about an enumeration of the lattice walk, and there are methods in your enumerative comparison, but I didn't talk about it today. And I talked about the kernel method, that is, we treat algebraic roots as formal series of T, and by considering the properties of these roots, and so we can solve the functional equation. And we consider the Riemann boundary value problems, and this is actually we treat the kernel as a algebraic curve, and also we consider the conformal mapping. So which is we working on the project plan, or maybe if we also consider Riemann surface, it is on some chats of a Riemann surface, and there's a conformal mapping that separates the unknown functions. And also we talk about something about elliptic function and about representing the solutions by the singularities of the elliptic functions. And also we talk about the relation between lattice walk and the inverse scattering method. We can see that so the lattice walk can be treated as an integrable model, and we can solve it by inverse scattering method. There are also many other methods, but I haven't talked today. So maybe we should, to end my talk, we should ask some questions. For example, can we solve the three-quarter plane on project X plane via conformal mapping and PVPP? And what about the large step walks? Because it depends on higher dimensional manifolds and also some more complicated symmetry. And what about the integral relation, the relation between integral phase model and lattice walk? Because in lattice walk, in our solution, we use algebraic roots to represent our solution, but in integral phase model, we use some different things. So what about the relation between these? And that's all about my talk. Thank you, and happy birthday, Professor Xu.
Thank you. We have questions?
I have a naive question. I thought I would understand more. How is an algebraic curve related to your lattice walk? This
Algebraic what? Curve?
Yeah, how do you get an algebraic curve? Because so there's many places resemble me or what I know, but somehow I haven't got the basic.
So it is a kind of.
Is it certain generating function?
Yes. So here the kernel here. It is, if you time x, y to it, it is an algebraic. It is a quadratic function.
Yeah.
Now you consider x and y. You treat this quadratic function as an algebraic curve, and you consider x, y on this curve.
Don't get it. So your basic model, you walk left, yes, right, up and down. So
yes.
And this is in your variables x, y, x inverse, y inverse. Yes. What is q of x, y, t?
Q is y.
It's generating function.
Yes.
Yes. And okay. So where is an algebraic curve here?
So algebraic curve is this kernel 1 minus t x plus y plus 1 divided by x plus 1 over x.
And it kind of encodes your walking rules, yes?
Yes, it's you can treat it as the symmetry of the walk.
Symmetry of the walk,
yes.
Okay. And it depends on a specific rule, yes?
Yes, it's So you can. So the idea is that this equals 0.
Yeah.
Then it is an algebraic curve.
You're also saying something on walks on the curve. What do you mean by that?
Works on the curve.
No.
No. The works doesn't. Works is on in the quadrant. Just our symmetry is on this curve. Yes.
There shouldn't be that many models.
Yes, there are many models because you don't need the work to be exactly this. Then they will have different curves.
Restricted.
Thank you. More questions?
Must your lattice walk be on an infinite plane? Can you do it on a translation surface where, it's a finite rectangle? So you have this grid, but then you glue the size by subtranslation.
Yes, I know what you mean. I believe that is some. I think I can do this. I mean, so the difference is we have different boundary terms. You can just project it on the plan because you glue the glue the upper and lower. So there will be a boundary term on the an extra boundary term on your on the upper part, which goes back to the lower part. So I believe if you consider this simple lattice walk, this will be something here. There is something here 1 minus x m is your height of. Yes. Yes. So actually, it is something like it's an integral phase model. So actually, I just asked for today about this because for integral phase model, we actually have two boundaries on both sides and let n into infinity. But the model I demonstrated here is this. So it has one boundary. The other part is free. So there are some difference, but I think still, but I believe that we can use the algebraic property of this kernel still can help us with the finite case.
Thank you.
Okay, I want to ask you, maybe it is not directly connected. Yes, you mentioned some Catalan numbers, some gig paths, and so on. Yes, there is topological interpretation of Catalan numbers and the same as gig paths as a triangulation, one-point triangulation of sphere. Yes. Wow. And in this case, very natural questions, what happens if we consider, for example, several points triangulations of sphere or paths on the Riemann surfaces of higher genus. In this case, there is some technique which is called the topological recurrence, which allows you in some special case to compute the generating functions for this kind of object. Do you have some multidimensional generalization of these things? For example, paths not on the plane, but on in the cube, for example.
Okay. Probably I first need to say one thing. I start from this this research on quarter plane lattice walk not from works on quarter plane, but from some polynomial model in physics. So it actually, if you consider a walk, so I think this one will be more familiar to integral systems that you have several numbers of direct walk, and it cannot cross each other. So from here to here. So also, the Yamasa equation can always also be treated as a treated as a walk from here to here. And for these two-dimensional cases, it can actually, if you consider the distance between each walk as a parameter, then it will be turned into a quarter problem, a walk in the quarter problem. So actually, what I'm going to do is trying to extend the result from quarter plane to high dimension. Yes. And another question you ask about Cantor numbers, it is, so Cantor number is a very special number, but I'm not sure on high dimensional what it happens, but Cantor number is actually the, so in two dimensions, if you consider the Hadamard product of two Cantor numbers, not Hadamard product, Hadamard product of the product of two Cantor numbers, that is Hadamard product of two the general functions. It is actually the exactly the second elliptic integral. Yeah, second kind elliptic integral.
Yes, in some sense, I had in mind not multidimensional Catalan numbers, but Catalan numbers related with topology, with triangulations. This is so-called the Catalan higher genus Catalan numbers.
Oh.
This is also related with the spectral curve, and there is some technique which topological recurrence, which allows to you count, for example, triangulation, not zero-dimensional sphere, but arbitrary dimension sphere.
Oh, okay,
Yes.
sorry. Okay, I see. You mean with higher genus? Sorry, I have no idea about this. I know it's the Cantor number where in high dimensional will reduce some properties of the elliptic functions.
High dimensional really has simple combinatorial interpretations,
Yeah.
but the higher genus Catalan numbers, it's really mysterious things. It is sometimes called by mirror Catalan numbers.
Okay.
So mirror symmetry. So what is the kind of mirror symmetry on your picture?
Mirror symmetry. So sorry, I'm not sure this part. Sorry.
Thank you. Okay.